equal to 0. So what should I substitute for df1? Tau dA1, right? Just like the same thing we did before. And then you realize this sum is in fact, you can write it as sum. So positive torque, which I don't have it, minus sum of all R tau dA from 1 to infinity is equal to 0. What is that sum? It's just a surface integral, right? It's just a surface integral. So in fact, that equation is identical if I write it like T is equal to take the sum to the right. Integral R tau dA over the surface. So take this sum, you get positive on the right, and convert sum to the integral, you get double integral. That's it. Now all you need to do is substitute tau in this equation and take the double integration. And I'll give a bunch of examples for that. I didn't say go yourself and go home and study yourself. So what I'm going to do, I'm going to just use the result we had before and expand it. So here, tau T, the torque is equal to double integral R. What should I substitute for tau? Assuming this is a Newtonian fluid, right? Tau was what?
Mu.
You go to your node, it was mu dy. And we said in the figure I draw in your assignment, this was delta, and this is small. So we can approximate the derivative by mu over delta, and this is the upper disk velocity. So at any point, what's the velocity here? R omega. The velocity is what? At any R omega. So you just put R omega minus the velocity of the lower plane, which is 0, it's fixed, divided by delta time mu. That's your tau. So substitute that tau here. So you get R right here. Instead of tau, you put mu R omega over delta. That's your tau. And then dA. What should I put for dA? Last class?
R squared.
R dr d theta, no square. R dr d theta. So that's for dA. Let me highlight it. That's for dA. And then this is tau. And this is R. See? It's just the same, and this is the series that will convert to integral because it was infinite. Equal to T. That's it. Now I have to do this integral. Well, I know that in the theta direction, I have uniformity, right? So this is not a big deal. I can say theta from 0 to 2 pi. But look, from R0 to R1, what's my viscosity?
mu1.
mu1. And from R1 to R2, what's my viscosity?
mu2.
mu2. So I cannot just say from R0 to R2. I have to break it down into R1 and then from R1 to R2. So this integral, I'm going to write it like this. Integral theta 0 to theta 2 pi. This guy, R from 0 to R is equal to R1. Right? What's the value of mu here? Mu1. So you get R times mu1, R omega, delta, R dr d theta, plus integral from theta 0 to theta 2 pi. Then R from where? R1 to? R2. The same thing, R mu, but this one is mu2. That is R omega, delta, R dr d theta. Now, This one, it's just to expand the integral. What do I get for this integral? Take this theta here, I'll just rearrange it here, d theta here. Can you bring the d theta out? You can separate it, right? Because r theta are not entangled, r and theta. So you can bring d theta here. One of the homework, the cone, you can't do that. You have to substitute the value for z versus y, and then take the integral. Convert double integral to single integral. But this is just simple. What about r dr d theta? Keep the rest of it here, except bring omega out. So bring omega out over delta. Right? The rest is r, and then mu1. Okay? What about the second integral? Just like that, omega, so mu2 omega over delta, mu2 omega over delta, so you get r cubed. And then the integral of r cubed is what? So write the final result here, mu1 omega over delta. This is going to give you 2 pi times, this is going to give you 3, and then r4. So you're going to get r1 to the 4 over 4 minus 0, which is 0, plus this guy is going to give you mu2 omega over delta, again r4 over 4, but look, you're going to get r2 4 over 4 minus r1 4 over 4. This is equal to G. Now you can rearrange, you can factor out omega from this relation, because I said find the relation between torque and omega. Factor out omega, so this is going to be 1, the entire thing times omega. Torque versus angular velocity. That's the coefficient of. It totally depends on R1, R2, viscosity of fluid, and geometry. It doesn't depend on torque and velocity itself. So that's the solution to the first problem. Solution to the second problem. How can I solve this? So this was, we did system, FED, we wrote equations, which was just one of them, was not null, and then we solve it. And then can you verify it? The torque should be positive. If you get negative sign here, something is wrong. If something is wrong, what do we do? Go back and double check everything. So this verify. Now we go to the second problem. What's my system here? Well, your system, you can choose this column of mercury as your system. But we did that last class, and we already derived the equation. And what was the equation? If you go back to your note, was the pressure difference between these 2 points, call this A and B. What was that?
It's a delta.
P, right, delta P was rho G delta H. That was the equation we got after keeping the system, writing equation, solving it, was the final result. So I'll just use that. So let's consider point A. For that, I can write pressure at A is what? Pressure at here, B, right? I'm just explaining that relation. Pressure at B plus the height of this times, which is rho mercury, times the density of this fluid, which is mercury, times the height between A and B, which is what? H2 minus H1, times G, constant of gravity. What do I have for PA? Can you tell me? PA is exposed to? This one is exposed to atmosphere.
It's going to be 101 kilopascal.
That's right. So this is 101 kilopascal. What do I have for PV? The pressure at B, point B is exposed to the chamber. Do I have the pressure at chamber?
No.
So that's the unknown. What should I substitute for that?
13,600.
And it's already in a solid. So 13,600. And what about this guy?
0.2 meters.
0.2. It's not 20. You have to convert to meter. So 0.2 meter or 20 times 10 to the negative 2. And this is what? 981. Now if you put 9.8, I accept it. If you put 10, I accept it. Right? The idea is not, this is not important. So let's solve for this guy. If you put in a calculator, you can, there's one equation, one unknown, and then you get PV. So PV is going to be 1 over 3 minus 0.2 81. So you get PV is equal to what? 74.3 kilopascal. Look guys, that's the pressure inside this vacuum. And if that gas is ideal, what can you write for that gas?
The ideal gas law.
That's right. P is equal to rho RT. Right? And that equation, you have the P, just PV, right? You have the gas constant, you have the temperature, everywhere the temperature is same. Then you can get the density. Then density becomes, solve that for density, PV over RT is equal to PV 74.3 10 to 3 over R, gas constant 260 in a SI unit times the temperature 28. Something is wrong here. Can you tell me?
It's Kelvin.
Plus
273.
Cover to 273.1. So put it there. You get your density of what? .383 divided by 260 times. So you want a density rho at point B, rho inside the chamber becomes 0.949.
Well,
Question?
I was a little bit off. 35.
That my original answer was like .0000 something. I'm like, I don't think that's right.
That's because I didn't do the centimeters, meters. That one I had no clue. I had zero clue.
That's what 1.63.
I just completely forgot about the PRT equation.
Oh, yeah.
I'm just
Luckily, that was in my notes. So as I was looking, it was obvious to me to see it, or like I could see it pretty obviously. So I didn't have to remember it. I just saw it. Daggone.